So now the speaker is A Mondal from IIT Madras, and he will be speaking on uniform subnorm bounds on average for Siegel custom.
Okay. I thank the organizers for the great opportunity. I will be talking about my joint work with my doctoral advisor Hugh Kramer on uniform subnorm bounds on average for Siegel cusp forms. So this was the structure of the talk. We go over some background, then state the results, then briefly define the strategy of the proof. So the heat kernel is an important ingredient of our proof. For that we use some harmonic analysis on semi-simple Lie groups. That comes next. Then there is some weight correction. We will come there, and finally in last section we conclude the proof. So subnorm bound problems, this was originally a problem in classical analysis where you have a Riemannian manifold of finite volume and a Laplace-Beltrami operator on that, and we are supposed to find spectral bounds of the eigenfunctions of this Laplace-Beltrami operator. This came up as problems in chaos theory for studying the eigenfunctions. More particularly, this gives a measure of mass equidistribution of the eigenfunctions. That a higher subnorm generally means that it's less equidistributed, and a lower subnorm generally means it's more equidistributed. So there were some classical subnorm estimates. This has been quite some time. This was done by Ziegler, Sauger, Hormander, etc. And these are on quite general Riemannian manifolds, but here the subnorm estimates on lambda, they are quite saturated because of the presence of sphere or positively curved manifolds. For negatively curved manifolds that we encounter in arithmetic settings, we are expected to have much better bounds than this. So in that setting, with normalized Hecke-Maas cusp forms, Ivanich and Sarnak in 1995, they showed that this bound comes down from 1/4 to 5/24, but the conjecture, Sarnak's earlier conjecture, this is coming from random wave theories in chaos, that the expected bound that we should be getting here is much lower than that, that is lambda to the power epsilon. But we are nowhere near this bound so far, and this is quite a deep conjecture because it implies Lindelof hypothesis for the Riemann zeta function. So that the problem of subnorm there getting intimately connected to number theory. And the other variant of this problem is if instead of Hecke-Maas cusp forms we have holomorphic Hecke cusp forms, then we have roughly k of weight k. So k plays the role of square root of lambda here, and we will come to what is delta k and etc. But for now there is kind of a correspondence between Hecke-Maas cusp forms, the bottom of the spectrum of Hecke-Maas cusp forms, and holomorphic cusp forms. And this is gamma is a Fuchsian subgroup, a cofinite Fuchsian subgroup in general. So some of the results will be for SL to Z only, so that I will mention, but most of them they will hold for cofinite groups. So the trivial bound, as we were seeing, it's lambda to the power 1/4. So k being kind of root lambda, this is the trivial bound by Rudnick, it was root k, and for this the assumption of Hecke structure is not needed. For co-compact groups, Das, Somodas in 2015, they brought down the bound from k power half slightly there, and for the non-compact case, for particularly gamma equal SL to Z, Zia in 2007 he brought it down quite far to k power 1/4, but I mean these last two results they all assume Hecke structure. Now coming to somewhat the easier problem, it's both easier and more difficult in two ways. What if we take space and an orthonormal basis for that with respect to the Peterson product. Then on average we get very optimal bounds for these quantities. So generally the bounds on the average case, they are considered easier than bounds on particular eigenfunctions. But in this procedure of Friedman, Jorgensen and Kramer, they don't assume the eigenfunctions to have the Hecke structure. So this is quite, the basis taken could be any basis, it's quite general in that sense. So for co-compact we get bounds for K, and for cofinite we get K power 3 by 2, which by Zia's result as shown in the earlier slide, this is optimal because that was the lower bound also. And furthermore this bound is uniform in the sense that if we can prove it for some gamma 0, then for all finite index subgroups of gamma 0 we also have this result. So if we can get it for say SL to Z for all the congruent subgroups, we have an automatic result here, and even more general discrete groups than that. So our work in this particular thing was to generalize it for the Siegel upper half space. So for the definitions, that Siegel upper half space, these are symmetric complex matrices with the imaginary part positive definite. We have the symplectic group acting on it, what we can call the matrix fraction linear transformation. And we take an arithmetic subgroup, which for us is something that is commensurable with the Siegel modular group, SP and Z. And cusp form is almost identically defined as in the rank 1 case for the elliptic upper half space case. That is holomorphic, there is a transformation behavior, and it's moderate growth in the cusp neighborhoods or boundaries in this case. We denote this space as skn gamma. Then similarly we create the average quantity for which we need the sup norm. So this was studied by Cogdell and Luo in 2011, that for compact subsets they got the result k power n times n plus 1 by 2, which was kind of expected from complex geometric arguments, that n times n plus 1 by 2, this is the dimension of the Siegel upper half space. So for the compact bound we expect this kind of result, that on weight aspect this average quantity should be bound by k power the dimension, because if we go back to Sarnak's conjecture that this is k power epsilon, so in calculating the average there is of course the space of the dimension is coming in. So what this average result, it proves Sarnak's conjecture on average. In general that was true for the dimension 1 case also, and for the Siegel upper half space case also. But still it makes finding bounds for the single forms, it remains as elusive as ever, but on average this gives good bounds. So Blomer in 2005 working with Saito Kurokawa and Ikeda lifts of elliptic modular forms into Siegel modular forms. So he came up with the conjecture that for the non-compact case, single forms with single Hecke cusp forms, they should have bound of k power n times n plus 1 by 4. He proved it for Saito Kurokawa lifts, and recently Abhishek Shah and his student Felician Comtat, they also targeted this problem for n equals 2. But even with very strong hypothesis, so these generally assume some very strong hypothesis such as the Grand Riemann hypothesis, and even then for single forms we are not really at the optimal case. So if we go to the average case, Hashimoto gave the dimension of this Siegel cusp form, the space of Siegel cusp forms. With that, this particular conjecture in the average case, the optimal bound should be k power 3n n plus 1 by 4. Das and Krishna quite recently they studied this problem. For n equals 2 they obtained the optimal bound, but for n greater than equal 3 their bound was somewhat off from the green line should be the optimal bound, The red line is the compact bound, and their bound was the blue one. So as n increases, that bound goes further from there. And our main result was that with almost identical setup, we found the cofinite bound to be the optimal bound, 3n n plus 1 by 4 for general n. And this is also uniform in the sense the earlier result by Jorgensen, Kramer and Friedman was that we fix a gamma 0 group, then all its finite index subgroups, for that we have the result automatically. So coming to the strategy of the proof, so these soups are on the entire space, but if we can confine them to the fundamental domain, then our work becomes much easier, because that is a finite, because our groups are cofinite, so then these quotients gamma by hn, they have finite volume. So on that we can do all sorts of spectral theory and all. So this Siegel-Kuss forms, they have the transformation behavior. We are just taking the absolute value on both sides, and we see that we need to find somewhat the soup norm of this absolute value, but it does not descend on the surface. So that is why we multiply it with this determinant y power k by 2 because of the transformation behavior of determinant of y. Then this function phi, it descends on the surface, but that makes the behavior of phi on acting of gamma. This gives this automorphy factor in front of, so instead of phi gamma z equals phi z that we have in case of general mass forms, we have here something called the weighted mass forms with this automorphy factor attached in the front. So we take the space of all such functions that behave in, that has this transformation behavior, and cut out from that the square integrable functions. And so generally the Laplace-Beltrami operator on the Siegel upper half space, we denote it by delta, but to account for this automorphy factor, Laplace-Beltrami operator on Hn is supposed to be invariant under the action of gamma. But because of that automorphy factor, we have to add this linear term here so that it becomes a weight, what we call the weight k Laplacian. And we would be doing spectral theory with this weight k Laplacian, which is essentially self-adjoint, and so it extends to a self-adjoint operator on the Hilbert space that we cut out from there. So this we established, this was one of the first results, that the minimum eigenvalue of these functions, they are given by nk by 4 n plus 1 minus k, and for the minimum eigenvalue, all the eigenfunctions of the weight k Laplacian, they take a particular form, that phi z has to be determinant y power k by 2 fz, where f is a Siegel-Kuss form. So that connects the arithmetic quantity Siegel-Kuss form on one hand with kernel of the delta k operator, Siegel mass Laplacian, which is induced by this f going to determinant y power k by 2f. And then we take the periodized heat kernel corresponding to the surface that has a spectral decomposition, as we have seen here multiple times during the workshop and also during the conference, that there are some discrete parts, there is a discrete part and there is a continuous part with Eisenstein series. Now we multiply both sides with the minimum exponential, this minimum eigenvalue, and take t tends to infinity. So only the eigenfunctions corresponding to the minimum eigenvalue, they survive. Everything as it is e power something negative times t. When we take limit t tends to infinity, everything else just goes to 0. And we have exactly that quantity on the right hand side, of which we want the soup norm. So this, we want the soup norm of this quantity sk gamma z, and we have this exponential something periodized heat kernel. So basically we estimate the heat kernel on the left hand side here to get soup norm bounds of sk gamma z. But there is a caveat there that heat kernel estimates are plenty abound, but one has to think about it that these estimates cannot be too crude, because even though we have heat kernel estimates for say kT Siegel upper half space, but when we are periodizing, it becomes an infinite series. So if the estimate is too crude, then when we take this infinite series, it will not converge. So one has to make this estimate somewhat, it has to be a very fine estimate. So construction of the heat kernel. So heat kernel on the Riemannian manifold X, this is the heat equation, and we want the fundamental solution of the heat equation. So on upper half space, this takes this particular form. This is for the weightless Laplacian, and what we must see here, that we go for the Laplacian, that is the heat corresponding to delta K. There is this correction factor added to it. So this is Chebyshev polynomials, that it is the same formula, but there is a correcting factor. This is what we call the weight K correction. So we would be using harmonic analysis on semi-simple Lie groups to first calculate the heat kernel, and then we will correct it with a term something like this to make it the heat kernel for the weighted Laplacian. Yeah, so there is a general procedure for calculating heat kernels on symmetric spaces. This was done by Ganguly. We have the general notation for here. We take the polar decomposition G, K, K and the Lie algebras. Omega is the Casimir element of the universal algebra, which descends to the Laplacian. We will be using that fact. So this is the spherical functions are the eigenfunctions of the Laplace-Beltrami operator, which are invariant on action of K on both sides, that is on that polar decomposition. Then the heat kernel can be obtained by first taking the spherical transform of the heat equation and then taking the inverse spherical transformation after solving an ODE. So this was done by Ganguly. And this C lambda, this is the Harishchandra function coming for the Plancherel measure here. So for our case, G is the symplectic group SPNR, and K is the intersection with the orthogonal group, which is isomorphic to the n cross n unitary matrix group. The crucial element here is to calculate the spherical function, which is for real groups quite a difficult task when it's in higher rank. For rank 1, it is much more easier. So instead what we do is that we use a method by Flenstedt-Jensen. So we first calculate the spherical function on the complex group, which is much easier to calculate. This is just ratio of two finite sums. And then we use this theorem by Flenstedt-Jensen that we go from the real group to the complex group to calculate the spherical functions. They are related by this integral. So basically we take the complex spherical integral on the right hand side, multiply it with the complexified K. So this G0 by K0, this is the SPNR by this the real orthogonal group. For K, that is the complex orthogonal group, and this U is the unitary group. So these are, U is the maximal compact of the complex G, but K is the complexification of K0 itself. So from the real orthogonal, we go to the complex orthogonal. That will be a non-compact space, and this is we are basically averaging the complex spherical function on that complexified orthogonal group to obtain the real spherical function. So with this we get the heat kernel for the weight 0 case. So these are diagonal matrices. So because they are bi-invariant on action of the orthogonal group, we only calculate it on the diagonals. And so on the right hand side, this formula is not completely explicit yet. So these R's, the entry to the diagonal on the upper side, so they are related to a different diagonal matrix called rho 1s, and this is related by this first line. So this is the semi explicit nature of this integral. So we could not, I mean, if one could solve this first equation, as in we could get rho as functions of R and Q, then we would have an explicit heat kernel, something that we get in the rank 1 case. But here this is somewhat impossible, because that tantamounts to getting the eigen decomposition in n cross n complex Hermitian matrices, which can't be done. And K here, this is the symplectic complex orthogonal matrices, as we said, and U, these are the symplectic unitary matrices. And these quantities, epsilon and delta, they come from the root structure of the symplectic group. So they look cumbersome at first, but once you look at the root structure, you see completely why they should come here. Then we come to the weight K correction, that we have the normal action of a Lie group on the functions of on the symmetric space. That is the first one, and in the second one we have the automorphy factor put in. So because of this automorphy factor, which for us is of this shape, so under normal action, the Casimir element omega, this descends to the Laplace-Beltrami operator delta. But for this automorphic action, so for that the Casimir operator descends to the single mass Laplacian of weight K. So keeping this in mind, we will just slightly make a correction to the heat kernel formula that we obtained. So we take, so O is the base point of the symmetric space G by K, and the functions are lifted to the group. Then the invariance on the symmetric space, Fx equal automorphic factor F of gamma x, this becomes a relation in the group, as this is invariant on gamma, and the automorphic factor rather shifts to the action of the orthogonal group. And for weight K correction, we simply need to, we keep the same integrand, just instead of d mu K, we replace it by this JKO automorphic factor times d mu K, which for our heat kernel formula means the same integrand. We just put a determinant HQ, so this is coming as the, so this JKO, if we calculate it out, it will come out to be this determinant, which from that formula for the heat kernel, one can bind here in terms of exponential and cos hyperbolic of the diagonal elements of R and rho. And then we periodize it. In now we with this estimate, the periodization on the right hand, it actually converges on compactor. So for the compact case, when gamma is co-compact and the surface M, which is the gamma quotient of the single upper half space, so on the left hand we have the periodized heat kernel, and the sum over the gammas, we are replacing it by an integral. Because there is a counting function argument that one can do here, this sum basically depends, because we have the heat estimate there. This sum depends on, if we take a, say, R ball around Z, it depends on how many gammas are there such that the distance between Z and gamma Z is less than R. So because this is a compact case, the distance between Z and gamma Z cannot be very close, in that then it will have cusps. But here, because it is compact, there are no cusps, so they can't be infinitely close, so they have certain minimum distance called the injective radius between Z and gamma Z. Because there is a minimum distance, we can estimate the number of such gammas with the volume of the R ball around Z that we took. So this is how we take the heat kernel and heat kernel for Hn, and we make an integral over the space variables R, and the heat kernel already had these Q variables. Then using this connecting equation, QR Q bar T equals U rho U bar T, we make the change of variables, put in the Jacobian, and now this integral is explicit. So even though our heat kernel integral was not explicit, once we make this space integration, now everything becomes explicit. And then these can all be calculated with a series of gamma integrals, which gives this kind of a k power n times n plus 1, and there is a t. The t dependence we remove by multiplying with a Laplace transform, which gives us the required compact bound. For the non-compact case, we make some limiting argument that because heat kernel decays also in space, we go that the distance goes to 0, and in that limiting case, this Sk gamma z, this takes this particular form. So the right hand side, this sum, this is what we need to estimate. So because our arithmetic subgroups, they are commensurable with the Siegel modular group, we now focus on one particular cusp which we can take as the standard picture for cusps at infinity. And so for the arranged eigenvalues, we take a neighborhood of the cusp where the highest eigenvalue is greater than some epsilon. And with a maximum modulus argument, what we can show is that in that neighborhood, the maxima is actually obtained at the boundary of this this neighborhood, which makes that for lambda n y less than epsilon. So this is where we are looking for the subnorm bound. So it's not in the cusp neighborhood, it's not too far away from the cusp. It is in the annulus between the cusp and the cusp neighborhood that we need to calculate the subnorm bounds. So in this region, we split this sum into the one without any parabolics and the parabolic sum. We have the standard parabolic matrices here. So these look rather complicated, but thankfully the highest contribution, it comes only from these translation matrices, and the one without any parabolic elements, that obviously gives the compact bound. So these translations, we put it in there and we again estimate it by a integral, which comes out to be this sort of a matrix beta integral, which was calculated by Hua. And from there we can show that this sum can be bounded by n times n plus 1 by 4, which with the n times n plus 1 by 2 already there, this gives the requisite non-compact bound. And for the uniformity, we take that these cusps lie over each other with a ramification factor of L. So to get the uniform bounds, we need to remove this dependence on L, the ramification index. So for the ramification index in the Fourier expansion, we have this L in the Fourier expansion. And where we took this epsilon, this was where to take the epsilon. So there we replace this k by C2n with kl, and in the matrix, this translation matrices, we have to replace the s by ls. Then one can show from the form of the integral that this l, these two l's coming from the two sides, they cancel out, and so we have a bound that is free from l, and that is our uniform bound. Yeah, so thank you. That was the talk.
We are running out of time, but if somebody has a quick question and the speaker has a quick response, we can.
And if you look at a Hecke basis, do you get anything better, or this is an optimal result?
I mean, for single eigenfunctions, generally all the results that we have seen, they are on a Hecke basis. For the average case, we don't really need the Hecke basis because our arguments are all geometric mostly. So
Bruno has proved that for the two modular group, we got a lower bound for all n.
for
The lower bound, you were working
Yeah,
with
yeah.
the Bergman kernel.
Yeah.
So
The-
you got the lower bound k bar and whatever the.
yeah, the lower bound, I mean, that is why these bounds are optimal, because on the
So he proved it for in general, and the upper bound also he got in many cases.
yes, I mean, but that was for the Hecke basis.
Yeah, well, because you can always assume it's a Hecke basis. I mean, not generally, I'm saying
That I mean-
there exists a Hecke basis. So
Yeah, I mean, there exists a Hecke basis, but when you are taking a basis, so Hecke basis is a very particular case, a very particular arithmetic case. For even in the study of arithmetic chaos, that if we can remove that assumption, Sarnak's conjecture, it is originally for any cofinite subgroup. So that would be better. That's so.
But I think Raghunathan correct, doesn't SPNR have the congruent subgroup property for n greater than 2?
Yeah.
SPNR has a congruent subgroup
Yes,
of it, right?
sure.
I mean, you're working with arithmetic lattices, I thought. So,
Yeah.
so that will always be a congruent subgroup or not?
I mean,
Yeah, so and then you can reduce to congruence at some level. It will come with that somewhere.
okay. I mean, for the average case, removing the Hecke dependence was, getting on average, and so proving Blomer's conjecture on average and removing the Hecke basis. This was some of our goals. So, for geometrically thinking, Hecke basis is not that important for us, but I mean it's a particular basis. For a particular basis, if these results are available, I mean in any case for n greater than equal to 3, these results are not proven by thus. So ours is better in that case also. But if the Hecke basis assumption improves this method, we have no problem. So.
Yeah. All right. Thank you. And maybe you continue the discussion after